Welcome. Most system design resources out there spend basically all their time just telling you what a specific tool is. They'll tell you what Redis does or explain the inner workings of Kafka. But they rarely, if ever, show you the actual decision tree that interviewers are desperately looking for inside your head. Well, today, we are changing that. Okay, let's dive into this explainer. Our goal here isn't to just memorize a bunch of popular tech stacks. Instead, we're going to build a first principles decision-making framework from the ground up. Because by the end of this, you'll be able to logically derive the absolutely correct architectural answers for literally any system, exactly like a senior engineer would.
So here's our roadmap for today. First, read versus write systems. Second, choosing your database. Third, caching strategies. Fourth, queues versus streaming. Fifth, real-time communication. And finally, number 6, the ride-sharing example. Let's kick things off with Section 1, read-heavy versus write-heavy systems. Before you even think about picking a single database or throwing a cache into the mix, you have to look at your read-to-write ratio. This is the fundamental first question because this single number drives roughly 60% of all your subsequent architecture decisions. And this brilliantly illustrates the massive divide between the two. If you're building a read-heavy system, say a news site or a Twitter timeline, you might easily see 100 reads for every single write. Your strategy here is pretty clear. Cache aggressively, use read replicas, and denormalize your data so that your reads are just an incredibly fast single lookup. But let's look at the write-heavy side. If you're building an IoT sensor ingestion pipeline with, say, 1 million events per second, caching won't save you there. You absolutely need to use message queues to buffer those massive spikes. You got to batch your writes, use write-optimized LSM tree stores like Cassandra, and you have to shard your data early on because a single node is inevitably going to bottleneck. Now, this brings us to our first major interviewer trap. So many candidates fail right out of the gate because they immediately shout out a database name and then just desperately scramble to justify it. Please don't do that. Flip the order. Identify the access pattern first. Let the simple fact that your system is read-heavy or write-heavy naturally eliminate all the wrong options for you. Moving right along to Section 2, choosing your database. Let's start with the big 3. You're going to choose a relational SQL database like Postgres when your data has complex relationships or if you absolutely need strong ACID transactions. Think of a banking ledger, right? In that scenario, eventual consistency could literally mean losing money, which means losing your job. On the flip side, you'd choose a key value store like Redis when your access pattern is always looking up by a single known key and you need sub-millisecond latency. User session storage is a classic example of this. And then you'd reach for a document store like MongoDB for something like an e-commerce product catalog. In that case, the data is naturally nested and the schema changes constantly depending on the product. Next up, let's talk about the more specialized stores. You'd need a graph database when the core value of your system is traversing multi-hop relationships. Like LinkedIn's People You May Know feature. It's like a giant puzzle of connections. Then you've got wide column stores like Cassandra. You choose this when you have massive write throughput and need serious horizontal scalability with absolutely 0 single points of failure. Finally, we have time series or lakehouse architectures like Delta Lake. You use these when you're dealing with immense volumes of append-only timestamped data, and you need to run both streaming jobs and large-scale batch analytics on super cheap underlying storage like S3. So, we put together this matrix that perfectly maps those 6 core database types to their exact specific needs. If you anchor these use cases in your mind, I promise you'll never struggle to confidently justify your database choice in an interview ever again. Let's jump into Section 3, caching strategies. In a system design setting, caching is never just a simple yes or no question. It is a highly strategic calculation of exactly where to store data and, crucially, exactly how to invalidate it when things change. First off, where does the cache even go? It could sit on the client side, it could be at the edge via CDN for your static assets, or it might live at the application level using something like Redis for computed results. But honestly, the much more important question is, how do you handle invalidation? You might use a simple time to live, or TTL. Actually, scratch that. If you have an e-commerce site where showing a stale price to a customer is totally unacceptable, a TTL won't cut it. You'd want a write-through strategy. That's where you update the cache and the database simultaneously, ensuring the customer always sees the exact correct price. And here is the big caching trap. Simply saying, "I'll add a cache," and then just stopping your explanation right there is a massive red flag. A true senior-level answer has to address the eviction policy, like least recently used, and you have to explain how you're going to prevent a thundering herd scenario. That's a nightmare situation where a sudden cache miss causes
thousands of requests to instantly slam your database all at once and completely take down your application.
Let's move to and see how this builds into Section 4, message queue versus streaming.
Okay, so this is easily one of the most frequently confused topics in all of system design, but the difference is actually incredibly straightforward once you see it. A message queue, think SQS or RabbitMQ, is fundamentally for task distribution. Imagine an e-commerce checkout. An order gets placed, a task is sent to the queue to send a confirmation email, a worker grabs it, processes it exactly once, and then poof, the message is deleted forever. Streaming platforms like Kafka, however, are totally different. They are for event fan-out. So think of a user following someone on a social app. That single follow event is published to a stream, and then multiple independent services, like the notification service, the analytics engine, the recommendation algorithm, they all read that exact same event at their own individual pace. Plus, with streaming, the data is actually retained, so you can literally rewind and replay history later.
The trap candidates fall into here is blindly name-dropping Kafka just because it's a trendy, impressive-sounding technology. Look, if you only have one single consumer and you don't actually need to replay your data, a simple message queue like SQS is actually the correct, much more operationally simple answer. You should only justify streaming when you have a specific, undeniable need for fan-out or replay capabilities.
All right, Section 5, real-time communication.
So if you're building a chat app or maybe a live dashboard, you're going to need a real-time transport mechanism. Let's quickly look at your three primary options. First up is HTTP long polling. Basically, the client asks for data, and the server just holds that connection open until it finally has something to send back. It's definitely not the most efficient way to do things, but it is absolutely perfect for legacy systems locked behind strict corporate proxies where you only really expect infrequent updates and you just need maximum rock-solid compatibility. Next, we have server-sent events, or SSE. This is a single, long-lived connection that is strictly a one-way street, server to client. This is the absolute perfect fit if you are building something like a live news ticker, a stock market dashboard, or if you're streaming AI text responses token by token. The server just continuously pushes updates down the pipe, and the client just sits there and listens.
Finally, the big one, WebSockets. This is a full duplex persistent connection, meaning both the client and the server can fire off messages back and forth independently at extremely high speeds. You explicitly want to choose WebSockets when you have high-frequency, bidirectional needs. Think of a collaborative document editor like Google Docs, or a live, fast-paced multiplayer game.
Now, let's bring it all home with Section 6, the ride-sharing example. Let's snap all these puzzle pieces together and synthesize this entire framework by architecting the core systems of a ride-sharing app. Now, what's really interesting about this slide is how logically it all flows. Step 1, access patterns. We know driver locations are hyper-write heavy, while trip payments need incredibly strong consistency. Step 2, databases. Knowing that, we'll use Redis with geospatial indexing for crazy fast driver location lookups, we'll use Postgres to guarantee atomic payment transactions, and we'll use Delta Lake to store all the historical telemetry for our analytics team. Step 3, caching. We'll definitely cache those computationally expensive nearby drivers' query results on a very short TTL. Step 4, messaging. We'll use an SQS queue for the simple point-to-point task of assigning a specific driver to a rider, but we'll use a Kafka stream for the raw GPS pings, so both our ETA service and our fraud detection service can read those exact same events simultaneously. And finally, Step 5, real-time. We'll use WebSockets for that sweet bidirectional live map tracking during the actual ride. Do you see how naturally that entire architecture flows when you just rely on first principles?
So if you take absolutely nothing else away from this, the crucial point is this: never, ever name drop a technology without immediately following it with the word because. Saying, oh, I'll use MongoDB sounds, frankly, junior. Saying, I'll use a document store like MongoDB because our product catalog features highly variable schemas that just won't fit into rigid SQL columns, now that sounds like a senior engineer. Supplying that because is the entire difference. And there you have it. You've got the definitive decision-making playbook. You now possess the structured framework needed to navigate access patterns, choose databases, plot out caching, handle messaging, and pipe real-time streams. The only question left for you is, now that you have this powerful playbook, what complex system are you going to derive from first principles next? Thanks so much for joining me on this explainer, and keep building.